It all started with an apple. Back in 1665, the outbreak of the bubonic plague forced Sir Isaac Newton to return home from Cambridge University. While at home, he saw an apple drop from a tree, which caused him to wonder why it fell straight down. This led to his groundbreaking work on two theories. Firstly, the universal law of gravity, which states that any objects with a mass have a force of attraction between them. And secondly, the laws of motion. Newton's laws of motion drew upon the Galilean reference frame as one of the earliest versions of relativity. In this version, time was constant and there was no limit to velocity, as Newton believed that all velocities were relative. For example, if you're standing still on the platform and you see a train pass by, it would have been fast, right? But if you were in another train that was going in the opposite direction, it would seem even faster. That's relativity. But there was a slight problem. You see, in the 1800s, Scottish physicist James Clerk Maxwell came up with the theory of electromagnetic radiation. This theory brought together electricity, magnetism, and light as different versions of the same concept, electromagnetic waves, which are the flow of energy containing electric and magnetic waves that travel at the speed of light. Maxwell stated that the speed of light is constant, about 300 million meters per second, and is the limit of how fast anything in the universe can go. This meant that Newtonian relativity couldn't be true, as it relied on the fact that there was no limit to velocity. Something was missing. To find it, we have to fast forward to the 1900s and an admirer of these two great minds, Albert Einstein. Einstein was able to find the missing piece by accommodating the two theories with his suggestion that instead of the speed of light changing relative to the observer, time could be relative. This gave birth to Einstein's special theory of relativity. In 1905, on his way home from work, Einstein was riding a tram and could see the Zeitblad clock tower and its hands ticking. He imagined what would happen if the tram were travelling at the speed of light, and using just his imagination deduced that the hands would freeze, and came to the conclusion that the faster you move through space, the slower you move through time. This led to the later discovery that space, which we're used to thinking of being 3D, is actually combined with time into a four-dimensional concept called space-time. Think of space-time as this invisible fabric that runs through the entire universe. Strangely enough, to understand this concept, we have to look back at gravity. Newton described gravity as a force that pulls objects with mass together. However, Einstein said that gravity changes the shape of the space-time fabric around an object. Therefore, any object with mass bends space-time around it. Picture a heavy object on a sheet or a trampoline. In the same way, Earth warps the fabric of space-time around it, causing it to push down on us and forcing us to stay on Earth. Remember, an object that's bending space-time is effectively bending time itself. So, time runs slower where there is more gravity. Or if you look at it in another way, where there is a larger bend in space-time. This is called gravitational time dilation. Also, it's important to note that the closer you are to the center of the Earth, the deeper into the bend of space-time you are, which is where time runs slowest. In 1971, Joseph C. Haffel and Richie Giachetti came up with an ingenious method to test this theory using extremely accurate atomic clocks on airplanes. One clock was placed aboard a plane that flew around the world twice. The other was left at ground level. When the plane returned, the times on the clocks were compared. The clock that had been aboard the plane was slightly ahead of the one that was left on the ground. Obviously, the difference was tiny. The plane would have to stay in there for a very long time for there to be a noticeable difference. For example, if the clock was set 9 kilometers above sea level when Earth formed about 4.6 billion years ago, today it would only be about 39 hours ahead of a clock that was set at sea level. And of course, there's an equation for this phenomenon. Let's take a look at it. First of all, T0, which is the proper time. This is the time recorded when the observer and the event are at the same point in space-time, which means they'd be experiencing the same gravitational force. Next, there is TF. TF is the time as measured where there's no gravity. The G is the universal gravitational constant, which is this. Don't worry about its value too much. And R is the distance from the center, or just the radius, of the object whose gravitational force the observer is experiencing. For us, that object is Earth. M is the mass of that object. C is the speed of light. Notice there are two main variables in this equation. the mass and the radius of the object. If you increase the mass and decrease the radius, two factors that would increase the gravitational force on the observer, time decreases. It slows down. Challenging beliefs and building upon existing ideas is what science is all about. Maxwell came up with a theory in an unrelated field that disproved Newton's theory, which had been seen as factual for 200 years. Then, Einstein was able to come up with a new theory that allowed for the two ideas to coexist. Gravitational time dilation has got to be one of the strangest revelations in Einstein's theories of relativity. Time has always been seen as a steady constant, but in reality it can be warped. However, no theory is set in stone, so who knows what other constants may actually be variables.